Did you know that one remarkable material is used to create luxury mattresses worth as much as $8,500? It is natural latex, a form of natural rubber known for its exceptional softness, extraordinary elasticity, and superior body support. But how does the milky white sap flowing from a rubber tree become such a valuable material? The journey begins on tropical rubber plantations, where carefully made tapping cuts release fresh latex into small collection cups. Because this liquid can coagulate quickly, it is promptly gathered, filtered, and stabilized before being transported to the factory. There, by changing the formulation and shaping process, the same latex can be transformed into a comfortable mattress, a thin glove that fits closely around the fingers, or the familiar eraser found in almost every pencil case. In this episode, Factron Process explores the complete technological journey that transforms natural tree sap into elastic products used around the world. Harvesting rubber latex is a technique that requires millimeter-level precision. A rubber tree usually needs about 6 years after planting before it is mature enough for tapping, because by then, the latex vessel system inside the bark has developed steadily. The worker uses a specialized tapping knife to cut a thin line along the trunk, usually in a slanted direction, so the cut can cross as many latex vessels as possible. The cut must be deep enough to reach the latex-producing layer, but not so deep that it damages the growth layer. In good tapping practice, the cut is often kept about 0.5 to 1 millimeters away from the cambium. Even a tiny mistake can reduce the tree's yield, cause tapping panel dryness, or take years for the tree to fully recover. The work usually begins early in the morning, when the internal pressure inside the tree is still high and the latex flows more easily. After the bark is cut, the milky white latex runs down a small spout into the collection cup below. Each tree may continue dripping for several hours before the latex naturally coagulates and seals the wound. A rubber tree does not feel pain the way humans do, but it does recognize injury in the way a living organism can. When the blade cuts into the bark, the white latex that flows out is not only a raw material harvested by humans, it is also the tree's own defense response, like a natural bandage sealing the cut. That is why workers usually tap the tree only once every 2 to 3 days, giving the bark time to recover and allowing the latex vessel system to regenerate more latex. With this careful rhythm, a healthy rubber tree can quietly produce latex for more than 20 years before its yield declines and it is replaced by a new generation of trees. Interestingly, rubber latex does not always remain liquid after leaving the tree. If it is collected early and preserved with ammonia, it stays milky white and can be used to make mattresses, gloves, and other latex products. But if it remains in the collection cup for too long, bacteria and naturally formed acids cause the tiny rubber particles to stick together, turning the liquid into a solid mass known as cup lump. Simply put, the same latex can follow two different paths. One is kept stable as a liquid, while the other is allowed to coagulate for use in solid and block rubber products. From the tropical rubber plantations along Guatemala's Pacific coast, freshly collected latex is transported to nearby workshops, where it begins its transformation into one of modern industry's most versatile raw materials. Every year, the world consumes around 15 million tons of natural rubber, and each batch can follow a different path. Latex preserved as a liquid may become medical gloves, mattresses, or elastic thread, while latex that is coagulated, rolled, and dried into sheets is used to produce tires, conveyor belts, shoe soles, and countless industrial components. These simple rubber sheets form a vital link between Central American plantations and the products that keep everyday life moving. Rubber gloves are made directly from concentrated liquid latex, which typically contains around 60% dry rubber. Ceramic hand-shaped molds are first thoroughly cleaned, heated, and dipped into a coagulant solution so that the latex can adhere evenly to their surfaces. Thousands of these molds then move continuously through a latex tank, forming a thin rubber film around every finger. Washed with hot water to remove excess proteins and chemical residues, and then vulcanized with heat to develop the required strength and elasticity. The glove cuffs are rolled into reinforced beads before each glove is stripped from its mold, checked for pinholes and defects, and packed. On large automated production lines, output can reach approximately 30,000 to 40,000 gloves per hour. After being filtered, the rubber latex is diluted to reduce its rubber content to around 12.5 to 16%, helping each batch coagulate with a more uniform thickness and consistent quality. The latex is then poured into shallow metal trays, where workers add an approximately 1% formic acid solution and stir gently to distribute it evenly. Under the effect of the acid, the tiny rubber particles suspended in the liquid begin to bond together. After about 3 hours, the milky white latex transforms into a soft, opaque mass that still contains a large amount of water. After coagulation, the rubber blocks are still thick, soft, and filled with serum water and traces of residual acid. Each block is therefore washed with clean water before passing through a series of rollers, with the gap between them gradually reduced to squeeze out moisture without tearing the material. With every pass, the rubber becomes longer, thinner, and more uniform until it reaches a thickness of about 3 millimeters. The sheet passes through grooved rollers that create its characteristic ribbed surface, helping prevent sticking, improve moisture release, and promote more even drying. The sheets are then washed once more to remove any remaining serum and impurities. The rubber sheets are hung on racks to drain before being transferred into a smokehouse for approximately 3 to 4 days, where the temperature is typically maintained at around 50 to 60 degrees Celsius. Below the drying chamber, firewood or wood chips are burned slowly, producing a steady flow of warm smoke that circulates around each sheet. The heat gradually removes the remaining moisture from within the rubber, while natural compounds in the smoke settle on its surface, creating the characteristic amber yellow color and helping protect it against mold during storage. The temperature must be carefully controlled. If it is too low, the sheets will dry slowly and unevenly. If it is too high, the rubber may darken or lose quality. By the time the sheets leave the smokehouse, they are dry, flexible, durable, and relatively uniform in color, ready to be inspected, graded. Once the rubber sheets reach the required level of dryness, their surfaces, color, and cleanliness are inspected before grading. Sheets of the same quality grade are stacked neatly and compressed in a hydraulic press to form firm, uniform bales. This packaging method reduces volume, limits deformation, and makes weighing, storage, and transportation more efficient. Finally, each bale is wrapped for protection and labeled with its weight, batch number, weight, and quality grade before leaving the facility for factories that manufacture tires, conveyor belts, and many other industrial rubber products. Leaving behind the sheet rolling lines and smokehouses, a portion of the liquid natural latex is sent to modern factories to begin a more premium transformation, becoming the core of a latex mattress. First, concentrated natural latex is pumped into a large mixing tank together with sulfur, vulcanization accelerators, foaming agents, stabilizers, and antioxidants. Each ingredient serves a specific purpose. Sulfur provides strength and elasticity. The foaming agent creates the porous structure, while the stabilizer prevents millions of air bubbles from collapsing before the material is molded. A continuous mixing system disperses all additives evenly throughout the latex, producing a smooth, uniform white compound. The formulation must be controlled very precisely. For every 100 parts of dry rubber, approximately 13.5 parts of additives are used. Even a small deviation can make the mattress core too hard, too soft, unevenly foamed, or prone to losing its shape during use. Next, the latex mixture is pumped into a metal mold fitted with small rods called pin core pins. These pins create a network of ventilation holes throughout the mattress core, improving airflow, reducing heat buildup, and increasing elasticity. The amount of latex must be carefully controlled to prevent empty spaces, overflow, or deformation. Inside a sealed chamber, the latex core is heated under pressure, allowing sulfur to form crosslinks between the polymer chains. This process transforms the soft, sticky latex mixture into a strong, stable, and elastic rubber structure. As a result, the mattress core can retain its shape, resilience, and cellular structure for many years without easily sagging or deforming. Once vulcanization is complete, the mold is opened and the mattress core is allowed to cool before removal. At this stage, the rubber is still warm, soft, and highly delicate. Uneven pulling or a strong impact could tear the surface, damage the ventilation holes, or deform the core. Therefore, workers or mechanical systems must lift and peel the mattress away slowly, evenly, and in a synchronized motion to preserve its shape, thickness, and surface structure. Leaving the mold does not mean the mattress core is ready for use. Soap, dissolved proteins, and compounds from the foaming process may still remain trapped inside its millions of air cells. Therefore, the latex block passes through a continuous washing system, where large rollers gently rotate and compress it, so that clean water can penetrate the entire structure. On some production lines, the core undergoes up to 5 washing and pressing cycles, with each cycle flushing out foam, residual chemicals, and the strong rubber odor without damaging the material's elasticity. This crucial step provides deep cleaning and improves the mattress's safety before it moves to the drying stage. A mattress core may look flawless on the surface, while still hiding weak zones or areas that recover poorly after compression. Before packaging, selected samples are therefore placed under an automated compression machine and repeatedly loaded to simulate years of body pressure. Sensors measure the depth of indentation, recovery speed, and any permanent deformation after each cycle. If the surface rebounds too slowly, shows uneven firmness, or develops lasting sagging, the product is rejected. Only mattress cores that quickly return to their original shape and maintain consistent support are approved for covering, packaging, and sale. After passing the full inspection process, the finished latex mattress cores are sealed in protective packaging that shields them from dust and moisture. They are then vacuum compressed or tightly rolled to reduce their size significantly for storage and transportation. Each package is labeled, sealed, and assigned a traceability code before leaving the factory for showrooms, hotels, and bedrooms around the world. The compressed latex gradually expands and returns almost completely to its original shape. In 2024, the global natural latex mattress market was estimated to be worth around $10.6 billion, showing how the white sap once collected from rubber trees has become the foundation of a premium sleep industry. Brands such as Avocado and Latexco have built their reputations around this material, turning its durability, support, and natural origin into products that can sell for thousands of dollars. Did you know that besides RSS rubber sheets, the rubber industry also uses a completely different raw material known as SBR/TSR, technically specified rubber? Instead of being rolled into sheets and then air-dried or smoked, coagulated rubber is shredded, washed, dried, and compressed into standardized rectangular blocks. From there, these blocks are transported to eraser factories, where they are transformed into a small but nearly indispensable item in everyday life. The refined rubber blocks are fed into a colander fitted with 3 to 4 large steel rollers. Rotating in opposite directions, the rollers continuously pull, compress, and spread the compound into a flat rubber sheet. The roller temperature is typically maintained between 60 and 110 degrees Celsius, while the gaps between the rollers are precisely adjusted to control the sheet's thickness. With each pass, Uneven areas and trapped air pockets are removed, allowing fillers and other additives to disperse uniformly throughout the material. The rubber strip is then cooled and cut to dimensions suitable for the forming line. This stage determines the eraser's softness, friction, and wear rate. Factors that directly influence how effectively it removes marks, how much debris it produces, and whether it damages the surface of the paper. The rubber sheets are placed into compression molds and heated to around 240 degrees Fahrenheit or 115 Celsius for nearly 20 minutes. Under heat and mechanical pressure, the rubber structure is stabilized, creating the softness and friction needed to lift graphite from paper without scratching its surface. Once the molds open, excess material is trimmed away, while the hot blocks are quickly immersed in water at approximately 70 Fahrenheit or 21 Celsius to stabilize their dimensions before being cut into individual erasers. A single large rubber sheet must now be transformed into tens of thousands of erasers with nearly identical dimensions. The white rubber sheets travel along a conveyor into an automated cutting unit, where the steel blades move in perfect synchronization with each advance of the material. Every cut must be swift and decisive, producing rectangular blocks with straight edges and smooth surfaces without deforming their internal structure. Excessive cutting force can chip or crack the edges, while insufficient pressure leaves rough and uneven surfaces. For this reason, conveyor speed, blade movement, and cutting intervals are tightly coordinated. The finished blocks drop onto a lower conveyor and quickly form orderly rows. Processing around 220 pounds of rubber per hour, the line can produce nearly 26,000 erasers per day, transforming one continuous sheet into thousands of small products shaped with industrial precision. Leaving the cutting machine, the eraser blocks are still nothing more than identical white products. They continue along the conveyor, where mechanical guides align them precisely before each one passes beneath the stamping head. During a brief pause, the logo, brand name, or product code is pressed directly onto the surface under carefully controlled pressure, strong enough to create a sharp, clear mark without denting, cracking, or deforming the rubber. Unlike an adhesive label that may peel away, this imprint becomes part of the eraser itself and remains visible throughout its use. With a capacity of around 5,000 to 10,000 pieces per hour, the line transforms thousands of anonymous rubber blocks into finished, uniform products ready for the market.